Hello everyone, my name is Weijie Jiang. It's my great pleasure to present the paper that I co-authored with my PhD co-advisor Zachary Pardos at UC Berkeley. The title of our paper is Evaluating Sources of Course Information and Models of Representation on a Variety of Institutional Prediction Tasks. As the utility of institutional data starts to become clear, data from institutions of higher education are quickly coming into focus for educational data mining and learning analytics communities. Recently, EDM has seen a more than doubling year-to-year in papers focused on prediction with large institutional enrollment sets. Actually, the use of institutional datasets dates back to the first EDM conference with the themes of classifying students and using students' enrollment data to acquire background knowledge for ITS. Here we summarize this body of work in terms of the most common data sources used and the most common prediction tasks. It's worth mentioning that the two empty cells here show that there's no work using the course content information, like the catalog descriptions for the grade prediction and the prerequisite prediction tasks. So this became a gap for us to fill in this work. Contemporary approaches to data mining institutional datasets in higher education have been exploring effective representational methods that factorize, embed, or vectorize courses into a space, such as matrix factorization, neural embedding models, graph-based models, and content-based methods. So in our work, we summarize and evaluate institutional prediction tasks in EDM across three dimensions. The first dimension is data. By data, we mean sources of institutional data. The second dimension is methods, basically models for representing students and courses. The third dimension is tasks, and here we mean institutional relevant prediction tasks. First, let me introduce the institutional data sources we use in this work. The first data source we used is enrollment histories and grades, which consists of anonymized students' enrollment histories and grade histories at UC Berkeley for 9 years. Besides this student data, there are also courses data with meta-information. The other two sources of data are both course content information, with course catalog a brief description of the course and course syllabus a more detailed chronological list of subjects and assignments that a course will cover. Next, let me introduce the second dimension, models for representing students and courses. In machine learning, representation learning is a set of techniques to automatically discover the representations needed for feature detection or classification from raw data. Here are the four models we either proposed or used in our previous work or designed in this work, and the data sources each model used to learn representations for courses, students, and even course grades. This whole figure illustrated how each model takes their corresponding data as input and generates course representations as model output. Let's start with bag of words. In natural language processing, each document can be represented by a vector of real numbers, and each number represents a term weight, which can be term frequency, a binary value, or TF-IDF weight. So we can apply these bag of words techniques to both our course catalog descriptions and syllabus to generate course representations. The second representation model is multi-factor course-to-vec. In our previous work, inspired by the word-to-vec model in NLP, we proposed a course-to-vec model to learn distributed representations of courses from students' enrollment records throughout semesters. Then, we incorporated more features of courses to the input of the course-to-vec model to enhance the learned course representations. The third representation model we used is LSTM, a variant of recurrent neural network. In our previous work, we used LSTM to generate course representations to students for the next semester. The input in each time slice is a multi-hot vector representing the courses taken in the corresponding semester, and the output predicts courses a student will take in the next semester. There are 4 weights of the input learned by the LSTM, and we combined them together to form representations of courses. The last representation model is a newly proposed graph-based model to construct a student course graph based on both enrollments of students and their grades for each enrolled course. For example, in this figure, we have 4 students and 4 courses. There's an age between a student and a course if the student has enrolled in the course. In addition, each age has a color representing the grade the student achieved for the course, and each course has its content information like catalog descriptions and the syllabus. Therefore, if we incorporate all these types of data into the graph, the network turns into an attributed multiplex heterogeneous network, for short, MHEN. Here are the main steps for training the MHEN model. First, we separate the whole network by age type, which is grade type. For example, we segregate the whole network into 4 subgraphs. Each subgraph is constructed by students and courses with a certain grade type. Then, for each subgraph, we use metapath-based random walk to generate node sequences. Next, we apply a skipgram model over the node sequences to learn their embeddings. For each iteration in skipgram training, the grade embedding of course node on a grade type is aggregated from individual embeddings of students that are its neighbors, and the individual embedding of a student node is aggregated from grade embeddings of courses that are its neighbors. A self-attention technique is also leveraged to combine grade embeddings on each grade type. Finally, we calculate the overall embeddings of courses nodes for each grade type and the overall embeddings of students. The last dimension we explored in this work is tasks, where these 5 institutional relevant prediction tasks were evaluated. Course similarity prediction is a way to test whether course representations contain important features of courses that could differentiate between similar and dissimilar courses. For example, these 2 courses can be deemed as an equivalency pair because of their very similar course content. For evaluation, we first fixed the first course in each pair and ranked all the other courses according to their cosine similarity to the first course in descending order. Then we recorded the rank of the expected second course in the pair and described the performance of each model on all validation pairs in terms of mean rank, median rank, and recall at 10. Enrollment prediction aims at predicting courses a student is going to take in the next semester based on their enrollment histories. In our previous work, we used a multi-hot vector to represent the courses taken by a student in a semester, and fed the multi-hot input to an LSTM to predict the student's enrollments for the next semester. Instead of multi-hot, we can also use the sum of course representations learned by other models, which usually have lower dimensions than multi-hot. Grade prediction aims at predicting grades a student will achieve for each enrolled course in the next semester based on their enrollment histories and grade histories. In our previous work, we also fed a multi-hot vector to the input of an LSTM, where the position of grades a student received for enrolled courses were set to 1 and other positions to 0. We can also replace multi-hot vectors with the sum of course grade representations learned by the student course MHEN model to reduce the dimension of multi-hot to a large degree. The next task is prerequisite prediction, which is essential to prepare students with the necessary foundational experience to learn and succeed in the advanced stages of their degree. In our previous work, we proposed a method to infer the prerequisite courses for any target course based on the LSTM grade prediction model we just introduced. Meanwhile, we could also use a simple multinomial logistic regression to build a supervised prerequisite prediction model, where the input can be any representation of a target course and output is a multi-hot of its prerequisite courses. In addition, we were also curious about whether course representations learned by different methods could encode course popularity information. So we use a simple multi-layer perceptron to predict average enrollment size per course using the different types of course embeddings we introduced in our method section. This will help to anticipate increases in the course demand and allow institutions to better plan room and teaching staff allocations. Before we move on, here we summarize each method with its corresponding data source leveraged and the embeddings they learned for each task. Now let's get into the experiment results. On the task of course similarity prediction, a simple bag-of-words representation of the course catalog description performed the best in terms of median rank and recall at 10. Enrollment histories provided the second best performing score using student course MHAN network-based embeddings, followed by multi-course-to-VAC. For the task of enrollment prediction, LSTM with a multi-hot input provided the best performance in terms of both metrics. In this task, using pre-trained embeddings from the network-based or multi-course-to-VAC approach worked less well than the multi-hot, followed by using the content-based representations as inputs. In grid prediction, the network-based method performed slightly better than the previous LSTM. On the task of prerequisite prediction, the network-based approach performed the best in recovering the ground truth prerequisite relationships found in our institutional data. The multi-course-to-VAC approach was not far behind. Finally, on the task of predicting the average enrollment of a course, multi-course-to-VAC provided the lowest RMSE. In addition, for course similarity prediction, we found concatenations of the bag-of-words-based methods and course-to-VAC-based method performed the best. The course attribute representations sourced from the student course MHAN model performed the second best among all single representation models. For grid prediction, we found the proposed student course MHAN model, though static itself, could map the knowledge levels of students on the features of courses with grade types to a certain degree. Besides, the sequential information of students' grades by semesters exhibited substantial importance. Lastly, the course embeddings with different grade types learned from the student course MHAN model helped increase the accuracy of grade prediction over the multi-hot input, no matter what the grade cutoff is. For prerequisite prediction, we found all the supervised models leveraged the prerequisite information performed better than the previous state-of-the-art inference model, which makes sense. And among all the prediction models, the course embeddings and grade embeddings learned from the student course MHAN model performed the best. In conclusion, in this work, we provided a comprehensive evaluation on the performance of different combinations of data and models on 5 institutional prediction tasks. In terms of institutional data sources, we introduced the large-scale syllabus data as a novel source of information about courses. We found syllabus data showed benefit over catalog descriptions on prerequisite prediction, grade prediction, and average enrollment prediction. It also complements the catalog description and enrollment data on the course similarity task. With regard to methods, we provided a novel application of a nascent graph-based approach for presenting courses and their grades, which is the first time that course grades could be embedded as distributed representations. For tasks, we found replacing multi-hots with pre-trained course representations in the LSTM input did not improve the enrollment prediction performance. However, replacing multi-house with pre-trained course grade representations from the student course MHAM model provided a small improvement in the grade prediction task. In the future, we will try to solve some limitations of this work. First, we aim to evaluate multiple institutions besides our current data to examine the generalizability of the proposed approaches. In addition, we will evaluate other classical models for these tasks and evaluate the learned representations on other institutional tasks in the future. Lastly, we will try to incorporate more varieties of data, such as the clickstream data in learning management system to enhance course representations. That's all for this presentation. Thank you for listening. If you have any questions or comments, please do not hesitate to contact us.